Hello and welcome to Data Science for Everyone. This is the second video of a two-part video series on how to perform supervised learning using the scikit-learn package in Python. The link to the first video is in the description and please check it out before watching this one. In part 1, we learned about the basics of supervised learning, the syntax of scikit-learn, how we can perform classification, regression, evaluate model performance, and learn cross-validation. In this video, we will be learning how to fine-tune models, how we can deal with missing data and categorical data, and also how we can evaluate multiple models to choose the right one. Let's begin. Let's revisit classification problems for a moment. In the last video, we discussed that one of the most common ways that we assess models' performance is by using accuracy, the fraction of correctly classified labels. But here's the thing. Accuracy is not always the most reliable metric. Imagine we are building a model to predict whether an email is a spam or not. Now, here's the catch. If only 1% of all emails in the data used to train the model are actually spam, our model will be very good at predicting emails that are not spam. The model will fail with high probability to identify emails that are actually spam. This is because it is focusing on the majority class, in this case legitimate emails, and completely ignoring the rare but critical spam emails. It is failing in its primary task, which is detecting spam. This is where the concept of class imbalance comes in. In real-world scenarios like this, one class, for example the legitimate emails, is overwhelmingly more frequent than the other class, which are spams. And when that happens, accuracy alone can be very misleading. In situations like these, we need to rethink how we measure and evaluate our model's performance. Let's look at how we can fix class imbalance to assess model performance. Let's say we want to evaluate a binary classifier, like the one we use for spam email detection. We train our model on our data using KNN, and this time we summarize the model's performance using a tool called the confusion matrix. A confusion matrix is a 2x2 grid that shows how the model's predictions match up against the actual outcomes. At the top of the matrix, you have the predicted labels, and on the side, you have the actual labels. By filling in the matrix, we can categorize the model's performance into 4 possible outcomes. True positives, these emails are correctly labeled as spam. True negatives, these are legitimate emails that are correctly labeled as not spam. False negatives, these are spam emails that were incorrectly labeled as not spam. And false positives, these are legitimate emails that were incorrectly labeled as spam. By the way, false positives and false negatives are called type 1 and type 2 errors respectively. So why is the confusion matrix so important? Using the confusion matrix, we can calculate a lot of different parameters. First, we can use it to calculate accuracy, which is the sum of the true predictions divided by the total number of predictions. It gives a general sense of how well the model is doing, but like we mentioned before, accuracy isn't always the most useful metric. Next, we have precision, which is the number of true positives divided by the total number of emails classified as spam, which are true positives plus false positives. In simple terms, precision tells you how many emails are labeled as spam that are actually spam. High precision means fewer legitimate emails are mistakenly classified as spam. The next metric is known as sensitivity, which is also called as recall. This is the number of true positives divided by the sum of true positives plus false negatives. Sensitivity or recall tells you how many actual spam emails were correctly identified by the model. High sensitivity means fewer spam emails are slipping through the cracks. Lastly, we have the F1 score, which is the harmonic mean of precision and sensitivity. It balances both metrics and gives them equal weightage. The F1 score is especially useful if you want a model that performs well across both precision and sensitivity. For instance, if you want to reduce both false positives and false negatives. A high F1 score means that a model is doing well at both precision and sensitivity, especially in situations where the dataset is imbalanced, like the spam detection, or fraud detection, or rare disease classification, etc. Let's learn how to use scikit-learn to generate confusion matrix. First, we'll begin by importing our data. We are using the pandas library to load a CSV file called churn-dataset.csv. The link is in the description below. Let's take a quick look at the first few rows. As you can see, the dataset contains 3 columns: monthly charges, which tells us how much a customer pays every month; tenure, which shows how many months they have been with the company; and churn, which is our target or response variable. 1 means the customer has churned and 0 means the customer has stayed. In this example, both monthly charges and tenure are our explanatory variables. We'll use them to predict whether the customer is likely to churn. This is a typical setup for a classification problem, and it's perfect use case for k nearest neighbors. To evaluate our churn model, we first import k neighbors classifier from scikit-learn.neighbors, test train split from scikit-learn.model selection, and classification report and confusion matrix from scikit-learn.metrics. We stored the explanatory and response variables in x and y respectively. Then we initialize our classifier as knn. We split the data into training and test sets, train our model on the training data. Finally, we use it to predict labels on the test set. This allows us to compute the confusion matrix. By the way, I have shown these in detail in the first video of this series. The link is in the description. To create the confusion matrix, we pass the test set response variable and the predicted response values to the confusion matrix function. After printing the matrix, we can see that there are 883 true positives in the top left and 195 true negatives on the bottom right. By passing the same arguments to the classification report function, we get a summary of all key metrics. It provides precision and recall, which is also called sensitivity, for each class. In this case, the churn class has a precision of 0.62 and a sensitivity of 0.39, indicating that the model is struggling to correctly identify customers who churn. The support column shows the number of true instances for each class in the dataset. Now we move on to the next segment, where we will see how to perform supervised learning using logistic regression in scikit-learn. In the first video of supervised learning, we used linear regression to model numeric response variables. But when the response variables are binary, such as 0 or 1, or logical, such as true or false, we use logistic regression. Even though it is called logistic regression, it is actually a type of classification and not regression. Logistic regression helps us estimate probability, or P, that a person belongs to either one of the two groups. For example, whether they have diabetes or not. Here's how it works. If P is greater than or equal to 0.5, we classify that person as 1, meaning that they more likely have diabetes. If P is less than 0.5, we classify them as 0, meaning they are more likely to not have diabetes. So, logistic regression turns probabilities into simple yes or no decisions, perfect for binary classification problems like this one. Let's look at the diabetes dataset that we had used to model classification in the first video. We'll start by loading the dataset into a pandas data frame and taking a quick look at the first few rows. By the way, the data is linked in the description below. The dataset includes several health-related features, things like the number of pregnancies, insulin levels, BMI or body mass index, age, and whether or not the person has been diagnosed with diabetes as the outcome variable. A value of 1 means they have diabetes, and a value of 0 means they don't. Using logistic regression in scikit-learn is just like working with most other models in this library. It follows a simple, consistent workflow. Here's a quick overview. We import the model. We start by importing logistic regression from scikit-learn.linear model. Set up our explanatory variable, which is glucose, and response variable, which is outcome. We create an instance of the classifier by calling the logistic regression function. Then we split the data into training and test sets. We train our model using the training data by calling the .fit method. And then we make predictions on the test set using the .predict method. By default, logistic regression in scikit-learn uses a probability threshold of 0.5. This means that If the predicted probability is 0.5 or higher, the model classifies the result as 1. Otherwise, it is classified as 0. But this threshold isn't fixed, and changing it can impact the model's behavior. So what happens when we adjust this threshold? To understand, we use something called a receiver operating characteristic or ROC curve. This curve helps us visualize how different thresholds might affect the true positive rate and the false positive rate. Here's what it looks like. The dotted line in the center represents a random model, a model that is just guessing. When the threshold is set to 0, the model predicts 1 for everything. This means that it catches all the positives but also labels all the negatives as positive. So both true positive and false positive rates are 1. On the other hand, when the threshold is set to 1, the model predicts 0 for everything. In this case, it completely misses all the positives. So both true and false positive rates are 0. As we vary the threshold between 0 and 1, we get different combinations of the true and false positive rates. Plotting a curved line through these points gives us the ROC curve, and this helps us visualize how our model performs across different thresholds. Before plotting the ROC curve, first let's predict the probabilities. To get the predicted probabilities for each instance, we use the predict-proba method from a logistic regression model and pass in the test features. This method returns a two-dimensional array where each row represents an observation, that is a patient, and each column gives the probability belonging to a class. The first column is the probability of not having diabetes, and the second column is the probability of likely having diabetes. For example, if we look at the first row, which is the first patient, the model predicts a 63% probability that the first patient will have diabetes. Since we're interested in the probability of diabetes, we are slicing the second column and storing it in a variable called ypreddiabetes. To plot the ROC curve, we import ROC curve from scikit-learn.metrics. We then call the function ROC curve and pass the test responses as the first argument and the predicted probabilities as the second argument. We then unpack the results in 3 variables: false positive rate, true positive rate, and threshold. We can then use the matplotlib plotting library to plot an ROC curve, which is shown in blue. So how do we actually measure how well our model performs based on the ROC curve? Ideally, we want a model that gives us a true positive rate of 1 and a false positive rate of 0, meaning that it catches all the positives and makes no mistakes on the negatives. That would be a perfect model. To summarize the performance shown in the ROC curve, we use a parameter called AUC, or area under the curve. AUC scores range from 0 to 1. A score of 1 means perfect predictions. A score of 0.5 means the model is guessing randomly. So the higher the AUC, the better the model is at distinguishing between two classes. To calculate AUC in scikit-learn, we import ROC AUC score from sklearn.metrics. Then we call the ROC AUC score function with 2 arguments, the true labels from a test set and the predicted probabilities from the model's predict-proba method. For our diabetes dataset, the model has an AUC score of 0.78, which means that the model is fairly good at making distinctions between diabetic and non-diabetic classes. Let's move on to the next segment where we learn how we can pre-process imported data before performing supervised learning. If you have watched my first video, link in the description, you'll know that before we start supervised learning, we need to check whether the data is in the numeric format and whether it contains missing values. More often than not, real-world data will have missing values and might not be in numeric format. In this part, I'll teach you how you can fix these issues before building your models. Let's start with how we can handle categorical data which are not numeric in nature. Say we have a dataset containing categorical variables such as job title. Since these values are not numeric, scikit-learn cannot process them directly. To make them usable, we convert each category into a numeric format by creating multiple binary variables, also known as dummy variables. Each new variable is an example that represents a specific job title. A value of 1 indicates that the observation falls under that job title, while a 0 means it does not. We create binary features for each job title. Since each person holds only one job title, each row in the dataset will have 1 in one of the columns and 0 in the rest. When we encode each job title, we have to make sure that there is no redundancy. Here we have 4 job titles. Let's say we choose associate as the baseline category. Then we only need to create 3 binary variables. We don't need the associate column at all. This is because if a row has zeros, for all the 3 columns, we can infer that the person is an associate. This approach is known as one-hot encoding with a reference category. This reduces redundancy and helps prevent duplication in models. Before demonstrating how to create dummy variables, let's import the movies dataset. I have the link in the description. After import, we can see that the genre variable is a categorical variable and is not numeric in nature. If we were to model using this variable, the model would fail. I'm going to show you how you can use the pandas library to create dummy variables for this column. We start by importing pandas, reading in the data frame, and then calling the getDummies method, passing in the categorical genre column. Since we need only 6 out of 7 binary variables, we set the drop first argument to true. When we print the first 5 rows, we see that pandas has created 6 new binary columns, 1 for each genre except the one we dropped. In this case, the action genre, which becomes the reference category. Now we need to add these binary variables back to our original data frame. To that end, we use the concat method, passing a list containing the original data frame and the new dummy variable data frame we created earlier. We also set axis equals to 1. Finally, we remove the original genre column using the drop method, passing the column name and setting axis equals to 1 again. Now we can start modeling with our dummy variables. Now let's see how to handle missing data. Previously we explored a modified version of the movies dataset. Now let's take a look at the original dataset, which contains 46,000 rows. To check for missing values, we'll use a simple method in pandas. We can chain these 3 functions together. The isNA method to find missing values, the sum method to count how many missing values are there in each column, and the sort values method to organize the results from least to the most missing. After running this, we discovered that each feature has between 73 and 131 missing values. There are 2 ways to handle missing data. One way is that you can remove them from the dataset. This approach is usually used where only a small amount of data is missing. Another way of handling missing data is through a process called imputation, where we make an educated guess about what the missing values might be and replace them. For numerical data, one common approach is to fill the missing values with the mean or median of the existing values in that column. For categorical data, like labels or names, we often use the most frequent values to fill in the blanks. But here's an important tip. Always split your data into training and test sets before you do any imputation. That way you are not accidentally letting information from the test set influence the model during training. This kind of mistake is called data leakage, and it can seriously mess up your results. In the next few slides, we'll look at how to handle missing values in a real dataset. In pandas, we can remove missing data using the drop_NA method. Inside, we pass in the subset argument, which includes the specific columns that we want to remove the missing values from. This tells pandas to remove any rows where those selected columns have missing data. So if a value is missing in any of the subset columns, the entire row gets dropped. After running this, if we check our data frame again, we'll see that it has no missing values. Let's walk through a basic workflow for imputing missing data. First, we import simple imputer from scikitlearn.impute. Since we'll be using different imputation methods for categorical and numeric data, we need to separate them. We split our dataset into xcategorical for categorical features and xnumerical for the numeric ones. We also keep our target variable stored as y. Next, we split both the categorical and numeric features into training and test sets, and we use the same value for the random state parameter to make sure that our target values stay aligned during split. For categorical features, we create a simple imputer and set the strategy to most frequent, which tells it to fill in the missing values using the most common category in each column. By default, simple imputer looks for missing values that are represented as np.nan. Now we call the fit transform function on the training categorical features. This fits the imputer and fills in the missing values. For the test set, we just call transform function, so we can use the same imputation rules learned from the training data. For numeric data, we set up a second simple imputer. This one doesn't need a strategy specified. By default, it fills in the missing values with the mean of each column. We use fit transform function on the training set to compute and fill in the missing values, and then use transform function on the test set to apply the same transformation. Next, we combine our imputed categorical and numeric training data using the np.append function, making sure to set axis equals to 1. So the arrays are combined side by side, column-wise. We do the same thing for the test data. Since imputers actually transform our data by modifying it, they're often called transformers in the scikit-learn ecosystem. We can also handle imputation and other pre-processing steps using a pipeline, which is a powerful tool from scikit-learn. A pipeline lets us chain together multiple steps like handling missing values, scaling features, and training a model into one streamlined workflow. To set this up, we import pipeline from scikit-learn.pipeline. In this example, we are working on a binary classification task where we want to predict whether a movie is action or not. Here's what we do. First, we drop any rows with missing values as long as they account for less than 5% of the dataset. Next, we convert the values of the genre column, our target or response variable, into the binary format. We use numpy.where method to assign 1 if the genre is action and 0 otherwise. Finally, we separate our explanatory and response variables into x and y, which we'll be using for modeling. To build a pipeline, we start by creating a list of steps. Each step is a pair. First, the name of the step as a string, in this case imputation and logistic_regression, and the second is the actual transformer or the model we will be using, which are simple imputer and logistic regression function respectively. We pass this list into the pipeline class to create our pipeline object. Next, we split our data into training and test sets just like we normally do. Then we fit the pipeline on the training data. This means the pipeline will automatically apply each step in order, in this case starting with imputing the mean and ending with the linear regression model training. Finally, we evaluate how well our model performs, typically by checking the accuracy on the test set. As we can see, the accuracy is 90%. In this segment, we learn about why we need to scale and center our data before we start modeling with them. Many machine learning models rely on some form of distance calculations to make decisions. So when one feature has a different scale than other features, it can end up having an outsized impact on the model's results. Take for example KNN or K nearest neighbors. It uses distance directly to figure out which data points are closest to each other. If one feature has values in the thousands and another is just a decimal, the bigger one can completely dominate the distance calculation. That's why it's important to make sure that all our features are on a similar scale. To do that, we can apply techniques like normalization or standardization, also known as centering and scaling. These methods adjust the values so that no single feature unfairly influences the model. Let's use the pandas describe method to get a quick summary of some key features in our movie dataset. This command gives us useful statistics like minimum, maximum, mean, and standard deviations for each column. Looking at the results, we can already spot some interesting things. Looking at the length column, which represents the duration of each movie in minutes, ranges from 1 minute to more than 800 minutes. The rating feature contains ratings between 1 and 10, and it can be decimal in nature. So from just a quick overview, we can already see that these variables have very different scales and units, which is something we'll keep in mind for later steps like normalization. Let's look at different types of scaling and centering. First, standardization, where we subtract the mean and divide by the standard deviation. This gives us a data with a mean of 0 and a variance of 1. Next is normalization or min-max scaling, where we subtract the minimum value and divide by the range. The result is data scaled between 0 and 1. Finally, scaling to -1 and 1, where we center the data around 0 and scale it within a range of -1 to +1. This is especially useful for neural networks that benefit from inputs centered around 0. In today's example, we will look at standardization. However, using scikit-learn, you can do whatever type of scaling you want. Let's learn how to apply scaling and centering to our movies dataset. First, we drop any rows with missing values in the length or rating columns using drop NA. Then we separate the explanatory and response variables. We split the data into training and testing sets using the train test split function. Next, we create a standard scalar object. Using it, we fit and transform the training data, and then we transform the test data using the same scalar. This is important to avoid data leakage. Finally, we print the means and standard deviations before and after scaling. We can also include a scalar inside our pipeline to pre-process the data. For example, here we create a pipeline that first scales the data and then applies k-nearest neighbor model. After that, we split our data into training and test sets, fit the pipeline on the training data, and use it to make predictions on the test data. When we calculate accuracy, we get a score of 0.88, which means that the model is correctly predicting 88% of the time. In this last segment, we will see how we can evaluate multiple models and choose the right one. Let's talk about a common but tricky question. Which machine learning model should I use? The answer isn't always straightforward. It really depends on your specific situation. But don't worry, there are a few key principles that can help you make the right decision. First, look at the size of your dataset. If you don't have much data, it might be better to stick with simpler models. They train faster and are less likely to overfit. Fewer features also help keep things simple. Next, consider the type of model you're using. Some models, like artificial neural networks, need a lot of data to work well. If your dataset is small, these models might struggle to make accurate predictions. Next, think about interpretability. Do you need to explain your model to make decisions to others, like stakeholders or clients? If so, go with something like linear regression, where you can clearly show and explain the influence of each feature using model coefficients. If your priority is model accuracy, you're okay with using more flexible model. Flexible models like k-nearest neighbors can capture complex patterns in the data. They also make fewer assumptions, like not assuming a linear relationship between inputs and outputs. So in summary, choose your model based on your data size, your need for explainability, and how flexible or accurate you need to be in your predictions. One of the great things about scikit-learn is that it gives you a consistent way to train and test many different models. That makes it super easy to compare performance across models. When you're working with regression models, you can measure how well they're performing using metrics like RMSE or R-squared. For classification models, you have several common metrics: accuracy, a confusion matrix, ROC curve. So a simple and practical approach is to pick a few models, choose a performance metric, and compare how each model performs. This gives you a quick baseline and helps you decide which models are worth exploring further. We're going to compare 3 different models used for binary classification to predict the genre of movies. The models we'll look at are k-nearest neighbors, logistic regression, and decision tree classifier, which is a new model that I haven't explained yet. Don't worry too much about it because the syntax is the same. We are just going to compare it to the other models. First, we need to import necessary libraries from the scikit-learn modules. Then we removed any missing values from our data. We set x and y as explanatory and response variables. Next, we split the data into training and testing sets. Then we scale the features using scalar, and then we apply the fit transform method on the training set and the transform method on the test set. Next, we're going to set up our models so that we can evaluate them using cross-validation. We start by creating a dictionary. In this dictionary, the keys are the names of our models as strings like KNN, Logistic Regression, and Decision Tree. The values are the actual model objects we have instantiated using scikit-learn. We also create an empty list called results. This is where we'll store the cross-validated scores for each model. Now let's loop through each model in the dictionary. We do this using the .values method, which lets us access the model objects. Inside the loop, we first create a k-fold object, which handles the splitting of our data for cross-validation. Then we use the cross-val score function to evaluate the current model. By default, cross-val score will calculate accuracy, which is what we want. The result is an array of accuracy scores, one for each fold. We add this array to our results using the append method. Once the loop finishes, we have a list of accuracy results for all the models. Finally, we create a box plot to visualize the performance of each model. We pass the results list and use the .keys method on our models dictionary to label the plot with each model's name. Once we generate the box plot, we get a visual summary of the cross-validation results for each model. Each box in the plot represents a distribution of accuracy scores across different folds of cross-validation. This helps us see not just the average performance, but also the consistency of each model. The orange line inside the box shows the median accuracy score. That's the middle value of the cross-validation results for that model. This gives a good sense of the typical performance. Looking at the plot, we can see that logistic regression has the highest median score compared to other models. This suggests it performed the best overall on our dataset. So based on cross-validation, logistic regression appears to be a top performer for this classification task. To evaluate our models on the test set, we loop through a dictionary using the .items method. This lets us access both the model's name and the actual model object in each iteration. Inside the loop, we fit the model to our training data, make predictions on the test set, and then calculate accuracy. Finally, we print out the accuracy for each model so we can compare their performance. In this case, logistic regression gives us the best results, at least when using accuracy as our evaluation metric. With that, we have come to an end of our walkthrough on how to perform supervised learning in Python using scikit-learn. We have covered how you can prepare your data, train different models, evaluate their performance, and choose the best one. If you found these videos helpful, don't forget to like, subscribe, and drop a comment if you have any questions or suggestions for future topics. Thank you for watching, and happy coding!